I guess we had to do it quite fast. So all you need to take from it is the fact that at least for b plus bigger than 1, you can do everything you want to do. You can perturb the metric so that the anti-self dual moduli space is smooth of the correct dimension with no reducibles in it. So now, having done the analysis, we can get back to the geometry. So there's one more piece of analysis, but it's very connected to the geometry. And this is where the geometry of the manifold will be reflected in the geometry of the moduli space, which is what you want. So to study the geometry of some weird-looking thing like the space of solutions of a PDE might seem a bit odd, but it does relate to the geometry of the original manifold. And that's through the compactification of the moduli space. So in the moduli space a priori is actually non-compact due to the conformal invariance of the Hodge star and therefore of the equations themselves. So we can conformally scale. Let's look at solutions on R4. You can conformally scale R4, just squash it, and the solutions of the equations, so the instantons, are invariant under that, so they can be pulled back under that. And so you can squash the instanton until it's concentrated more and more around one single point, say. So if I plot a graph of the, so if this is R4 and this is something like the norm of curvature squared pointwise, then I can do a conformal transformation to make this look more like this. Sorry, that should be higher than that. So that there should be the same area underneath the 2 because that's the second Chern class. Okay. So it turns out that the moduli space of instantons on S4, for instance, is the open ball B5. So the closed ball, the natural compactification, corresponds to the boundary is S4, this is B5. The origin here corresponds to some kind of symmetric instanton, SO5 symmetric, SO5 symmetric instanton or solution. That's the one with no peaking at all, so it's completely uniform. And then the boundary corresponds to Dirac delta sort of instantons, which are concentrated entirely at one point, at this point. And so the geometry of the moduli space reflects the geometry of the force sphere. So we can go from, we can glue in an instanton at a single point with the Dirac delta second Chern class. And then as you go in, it's becoming more and more smoothed out. So we're going from this picture to this picture by going in to the moduli space that way. Okay. So we have to allow, in order to compactify, we have to allow these so-called ideal connections with Dirac delta singularities in trace of F wedge F. And it's here that the estimates we have and the natural topological bounds giving L2 bounds on the curvature become very important, and that's where that's why we have compactness. And it's because each one of these Dirac deltas which bubbles off takes off one piece of C2, and C2 is only finite, so it can only happen a finite number of times. You can't have an infinite number of these bubbles. But I'll explain that. I'll explain why that is in a second. It's because of this analytical theorem of Uhlenbeck from something like 82, which says that if we have a sequence of connections of anti-self-dual instantons, then they converge weakly in the following sense. So this C2 form here converges as a current to a smooth 4 form away from a finite number of points. And at those points we have Dirac deltas. And away from those points, let's get my stick. Oh, there's a better stick. Away from those points, up to gauge transformation, the connections, we can assume that the connections actually converge to another anti-self-dual connection. So this is some kind of compactness result away from the points. But this is called the removal of singularities theorem. This is the key bit. This anti-self-dual connection away from the points extends uniquely over the points to a smooth anti-self-dual connection. So we can remove these Dirac deltas, we can pinch them off, and get a connection on a bundle with less second Chern class. So for each Dirac delta we pick off and we remove the singularity, we get a bundle with second Chern class reduced by that number of bubbles. These things are called bubbles by analogy with minimal surfaces. So there's a new underlying bundle. In this case, it would be the trivial bundle, because I started off with C2 equals 1. I pop off this Dirac delta, and I end up with something with C2 equals 0. And we said very early on that something with C2 0, and C1 0 in this case, which was anti-self-dual, actually had to be flat. So we end up with the trivial bundle with C2 equals 0 plus a Dirac delta. And we can't go to C2 negative because of these topological bounds. We saw that very early on, that C2 of an anti-self-dual connection had to be positive. So we can only do this a finite number of times. So this K is bounded by C2 of E because this has to be positive. So we end up being able to, is that clear what's going on there? So we pop off these bubbles and we still get an anti-self-dual connection underlying what remains. So in other words, we can compactify the moduli space. Inside, we have to take copies of these ideal connections. So this is a connection on a bundle of one less Chern class, but with one bubble. So this is a point, this is a curly M, this is the moduli space. So this is, point in here is an anti-self-dual instanton on a bundle of second Chern class one less. And then this is a point of the original manifold where I'm going to insert the bubble, the Dirac delta curvature. So there's a local model for that coming from R4, from this description, and we just glue it in. And then here, again, we've got 2 less units of charge of second Chern class and 2 bubbles, and so on, all the way down. So these are called something like small instantons in physics or something. But this was from the early 80s. So this topological L2 bound on curvature is crucial because it forces, because this underlying bundle here always has positive second Chern class because it has an anti-self-dual connection, it means that the number of bubbles can never be more than the original second Chern class. So it can be at most K bubbles. Okay, so using this, you get the first example. So this is the very famous Donaldson's thesis from 1982, or 1983. So we take the case where B plus equals 0. This is the case where we couldn't get rid of reducible connections, if you remember. So we can't perturb the lattice of anti-self-dual 2 forms. No. We can't perturb the lattice of integral 2 forms, so first Chern classes of line bundles, away from the anti-self-dual 2 forms. So we do get some anti-self-dual line bundles, which, when we add them to their inverses, gives reducible anti-self-dual connections. We do get some of those. But let's consider that case. So we can't avoid them. But otherwise, we can, using all our transversality results, perturbing the metric, we get a smooth, compact moduli space. And Donaldson considered the case where the second Chern class was 1, so you can only get 1 bubble, and it had dimension 5. This was from the Atiyah-Singer index formula I gave earlier. What are the reducibles? Well, they all come from line bundles such that this thing has second Chern class 1. But that's the statement that the first Chern class squared is minus 1. Remember, C1 of this times C1 of this is C2 of the whole thing. So, in other words, for every first Chern class, every integral second cohomology class with square minus 1, we get a reducible connection. So for all these things, we get a reducible connection. Because remember, H minus is the whole of H2. There's no H plus here. So there's no self-dual harmonic 2 forms. They're all anti-self-dual. So as I discussed before, from that what we get is a 6-dimensional moduli space locally around these points divided by S1, which gives a cone on P2. So a cone on S5 divided by S1. So we get this cone on, we get all these P2s here, take cones on them. Here's the moduli space, and it's compactified by adding in these bubbles. So for every point of the original manifold, we get a bubble. And a theorem of Taub's, which I haven't described, says that you don't end up in the following situation. The theorem of Taub says that when you compactify the moduli space, you do indeed get the space of all the bubbles. So you do not get this situation where the moduli space looks like this, and then where its natural compactification just looks like this, and it's smaller than the whole of M. Taub's proves that in this situation, you can glue in any ideal connection. You can actually then perturb it to be a genuine connection. So from any point out here, you can smooth it slightly to get in the moduli space. So in other words, the moduli space reaches all of this compactification. That isn't true in general. So we really do have this picture here. And then Donaldson used the geometry of this to prove his first result about four manifolds. So what you do is you chop off those cones, just chop the tops off those cones, and you get CP2s. So you get a cobordism from the original manifold to n copies of CP2, where n is the number of integral classes with square minus 1. Well, what that says is the signature of a manifold, which is, in this case, because there's no B plus on P2 or on the manifold, in this case the signature is just that the dimension of H2, the dimension of H minus. So this is B minus. The number of self-dual harmonic forms is actually invariant in this case under the cobordism. So in other words, you get an entire B minus of P2s up here. Well, what that says is that the second cohomology of M, the anti-self dual H minus, all of the second cohomology of M, is generated, in fact, we know it's generated over the real numbers by classes of square minus 1 because everything is anti-self dual. B plus equals 0, so all of these classes are anti-self dual. But this result says actually it's generated over the integers by classes of square minus 1. Okay? Because for every class of square minus 1, we got one of these P2s. And that says that the intersection form is actually standard. So that says the intersection form looks diagonally like minus 1, minus 1, minus 1, minus 1. So we can find all these classes which are orthogonal to all the other classes and whose square is minus 1. And that's not actually true of negative definite intersection forms. So by result of Friedman, topological non-smooth form manifolds don't have this property. So there exists topological form manifolds which have no smooth structure, so you can't start doing gauge theory on them. And from this, you can prove, for instance, there are non-standard R4s. So there are things which are homeomorphic to R4, but with a completely different smooth structure. They're not diffeomorphic. Okay. More generally, and in the case where B plus is bigger than 1, we can have invariance of four manifolds from these moduli spaces by integrating cohomology classes over them. So the way you produce cohomology classes is by the standard method of the moduli space times the manifold. The moduli space is supposed to parameterize vector bundles on the manifold, so there should be a universal bundle over this whole thing, which restricts at any point here E times M to the vector bundle E over M. So there should be a universal bundle over here. There isn't quite because of these stabilizers. So there's a universal bundle up to the action of plus or minus 1. You could go around a loop and find that your bundle has been switched by minus 1, and so it doesn't glue correctly. So what you end up with is actually a projective bundle. So this exists, and this exists, but E itself might not exist. But that doesn't matter. That's enough to define the second Chern class. So taking characteristic classes of these things, we get cohomology classes on M times M. And so Donaldson uses this to produce cohomology on the moduli space itself. So this is Donaldson's mu map. It takes the second homology of the manifold and produces a second cohomology class in fact, the space of all connections is curly B, all connections modulo gauge, but in particular by restriction into the space of connections on the moduli space. And the map is the following. You just take the slant product with this second Chern class that I defined before. So if you don't know what the slant product is, I can tell you what this map is in a different way. So I'm supposed to take a homology class on the manifold and produce a cohomology class on the moduli space. That cohomology class I compare with a homology class on the moduli space. So in other words, given a homology class here and a homology class here, I should be able to get a number. So given A in here and B in here, the number we get is this. So this is a homology class on the product, and we evaluate the second Chern class, the universal bundle over it. Okay, so that's an obvious map to produce cohomology from the geometry of the original manifold, and then we just integrate these classes over the moduli space. Actually, they're defined, as I say, on all of the space of all connections modulo gauge, at least the irreducible ones. The star means remove the reducible ones. And they also extend over the Uhlenbeck compactification because it's all done so naturally. And the Donaldson polynomials are integrals of these classes over the moduli space. So we work with B plus bigger than 1. You'll see why in a minute. So we can choose because B plus is bigger than 0, we can choose a generic metric to make this moduli space smooth of the right dimension. Then the compactification is a little tricky. So basically, you have to add these loci on of ideal connections, and what you need is them to be small. You need them to have codimension at least 2, so that this way the homology class of the moduli space is well defined. So the compactification doesn't affect the fundamental class of the moduli space. So that can be done. That's easy to control because we can choose a generic metric, so we can control all these lower dimensional moduli spaces, which we add bubbles onto. Except the one we can't control is obviously the trivial moduli space, where this is 0, so just the flat connection. We can't perturb the flat connection away. However much you change the metric, it doesn't affect a flat connection. The flat connection equations don't depend on the metric. So we have to work, there's just one technical condition to ensure that the flat connection, which is 0-dimensional, even though it might sit in a moduli space of virtual dimension, minus 10 or something, it's always actually 0-dimensional. So we have to make sure that this moduli space here, when k equals I, is smaller than the dimension of your full moduli space minus 2. So that's this condition here. So this condition says that the compactification is small. So we have a fundamental class of our moduli space. And now, given a bunch of elements in H2 of the moduli space, because we're dealing with 2 forms, they all commute, so it might as well be a symmetric power of elements of H2. We apply mu to each of them, wedge them all together, get a class in here. This is the dimension of this, so we can then integrate it. And for B plus bigger than 1, the result is actually invariant of the choice of metric, because a 1-parameter family of moduli spaces is also smooth, providing a cobordism between one moduli space and the other. So because they're cobordant, they're homologous in this space of all connections. Because they're homologous in the space of all connections, if I integrate a cohomology class over either one, I get the same result, because the cohomology class also extends the space of all connections. Okay, so these 2 moduli spaces given by 2 different metrics are actually homologous, and so sorry, that should say in B star. So the whole point is we can avoid the reducibles in a 1-parameter family so long as B plus is bigger than 1. And so nothing depends on the metric. We get invariance just of the differential topological structure of the manifold. And those are Donaldson's polynomials. And these turn out to be incredibly deep invariants. Well, the first result says they look pretty rubbish, actually. But this will be good later on. So they're actually 0 for any connect sum. We'll show they're non-zero in certain cases in a minute to use this theorem. So roughly speaking, that's easy to see. So if you have a connect sum of 2 manifolds, then what you can do is you can choose a metric, and you can make it generic at the end by perturbing it. But you can choose a metric so that the connect sum looks like this. So we have one manifold M1, take a small 3 sphere out of it, and glue it to sorry, a small 4 ball out of it and glue the S3 boundary to M2, you can stick in a very long, thin neck between the two. And then, as you might expect, instantons tend to concentrate on this side or this side. Or that sort of partition of the moduli space merges over when they start passing down the neck. So what you get is that, roughly speaking, the moduli space, at least over a big open set, looks like a union of pieces. This is the piece where we have K1 units of charge on this side. So we're gluing an instanton here to an instanton here with K1 second Chern class on this piece and K2 second Chern class on this piece, where the two add up to the second Chern class. Okay, so it looks like this, a union of all these pieces where you have different units of charge on either side, and they join where the units of charge flow down the neck. Times by SU2, this is how you glue the instantons over the neck. How you glue these SU2 bundles over the neck. And the point is that we're integrating these mu classes coming from homology classes or cohomology classes on the manifold, which just splits into the cohomology of this piece and the cohomology of this piece. So those indeed see this moduli space and this moduli space, as we've seen, and those give you sort of Donaldson polynomials here and Donaldson polynomials here. But they don't see this piece. They're completely trivial on this piece. So you'll always get 0. So let's explain that in more detail. So we're integrating these cohomology classes. By Poincare duality, we can think of this as, well, these spaces aren't necessarily smooth, but you can think of this as intersecting some classes, some homology classes on the moduli space. So we're just intersecting homology classes on the moduli space. Okay? And by doing that, we eventually cut down to the case where the moduli space is 0-dimensional once we've intersected enough of these classes, and then we just count the number of points. So that's the Donaldson polynomial. But this splits into two parts where my homology classes are either concentrated entirely on this side or entirely on this side. And we cut down until we get something 0-dimensional. That means it must be 0-dimensional here and 0-dimensional here, but then that would give you something 3-dimensional. So it actually must be some dimension here plus some dimension here, where the sum of the dimensions is -3. So at least one of them has to be empty. I don't know how clear that is. So you're intersecting these classes, but the problem can be divided up into two different parts. The classes can be pushed onto the two different parts of the moduli space. And so you intersect these classes until you get some class of some dimension here, some class of some dimension here. The dimensions add. And we're cutting right down until we get to 0 dimensions. So the sum of the dimensions here plus sum of the dimensions here plus 3 equals 0. So in other words, one of the dimensions must be negative. So one of these intersections, here or here, must actually be empty. So you get 0. Because that's what the definition of the Donaldson polynomial is. You produce these homology classes on the moduli space, and you intersect as many of them until you get down to something 0-dimensional. That's the definition. Then you count the number of points. That's what integration of cohomology is dual to under Poincare duality. So you just cut down until you get to something 0-dimensional. But if you're going to, when you do the cutting down, it splits into these two different parts. And so when you do the cutting down to something 0-dimensional, it's of the form, your 0-dimensional thing is of the form something in here times SU2. Well, 0-dimensional things clearly don't look like that unless they're empty. Okay. So I just mentioned this. I don't really know any four-manifold topology, but here's one theorem that I nicked from Donaldson's book. So two simply connected, this is a classical theorem of the 60s of Terry Walls, that two simply connected four-manifolds, I'm always in the simply connected case here to make things simple, with the same signature are actually diffeomorphic stably after you've added some S2 times S2s. So if you're going to see subtle invariants, which are better than the signature and better than just standard homological invariants, these invariants are going to have to be unstable. Once you connect some with S2 times S2s enough times, the invariants are going to have to become trivial because they're not going to detect anything. So this is sort of what this theorem of Donaldson's is in keeping with that. So this is sort of to be expected. that you get an unstable invariance. Wall's theorem says they should eventually be unstable. Donaldson's theorem says they're immediately unstable when you connect some manifolds. I hope I mentioned both of these manifolds have to have B plus bigger than 0. Good. But the invariants don't always vanish. So the other case, we mentioned that the anti-self dual equation has a good interpretation as the Hermitian-Yang-Mills equation if you're on a Kähler surface. So in fact, if you're on a complex surface, simply connected complex surface, up to deformation, it's actually projective algebraic. And so now we can describe the moduli space by that theorem of Donaldson-Uhlenbeck-Yau I was talking about before, in purely algebrogeometric terms, in terms of stable vector bundles. So it can be constructed algebrogeometrically. It's very naturally a projective variety itself, or at least quasi-projective. Then you have to compactify it using these singular sheaves. Those correspond to the bubbles in the vector bundle case. So you have slightly different compactification, but it doesn't matter. It's still small and so on and so forth. All the mu classes extend over it. Everything's fine. And what you find is that the mu map applied to your Kähler form is itself a Kähler form. As I say, suppose this is a projective algebraic variety. You can apply the mu map to the first Chern class of the line bundle, and what you get, the ample line bundle, what you get is the first Chern class . So in particular, combining the two theorems, you find that complex surfaces can't be written as connect sums, where the pieces both have B plus bigger than 0. They of course, often can be written as connect sums in one nice complex way, which is if you blow up a complex surface, you get another complex surface, and that operation of blowing up is actually a connect sum, but with CP2 with its opposite orientation, and that has B plus equals 0. So this theorem doesn't apply to that. So it's a very sort of optimal kind of theorem, but not completely optimal, as we will see in the last lecture when we do Bauer-Ferruta invariance, which refines this connect sum. So to give you an example, you take a K3 surface, and you can look at its intersection form, so the matrix of intersections between two cycles, and you find you get some crazy nonsense here, the E8 lattice, whatever that might be, plus 3 hyperbolics, where hyperbolic is just the standard intersection form of S2 times S2. It's just this. So take a basis of one S2 and the other S2. Neither intersects themselves because they're just fibers of a vibration, but they each intersect the other. So you might ask, because the intersection form splits off 3 lots of the intersection form of S2 times S2, you might ask whether the K3 itself splits off S2 times S2 as a connect sum. If it did, then you would get, that's what the intersection form of a connect sum would look like. But Donaldson's results show that that can't be true. Because the Donaldson polynomials of the K3 surface don't vanish, but the Donaldson polynomials of this connect sum would vanish. And the same theorem is true of symplectic manifolds, but the analysis is hideous, and so to do that you have to go to the Seiberg-Witten equations where the analysis is easier. Excuse me. That's supposed to lead naturally into lecture 4, but a small matter of lecture 3 to do first. Are there any questions about, so that's the end of, they're just some simple examples. In gauge theory, I wanted to give some kind of flavor of the analysis involved and how hard it is. and some of the problems it can solve. Some of the problems also it can't solve. As I mentioned here, K3 connects some K3 that has intersection form 4 lots of this E8 lattice and 6 hyperbolics. And you could ask whether that can split off an S2 times S2. And Donaldson theory tells you nothing about that because, of course, the invariants of this thing vanish. And the invariants of anything with a S2 times S2 splitting off also vanish. So you don't reach any contradiction that way. So you don't know. But it turns out that the Bauer-Ferruta invariants, which I'll discuss in the last lecture, can answer this question. Also, the analysis, as you can see, is very, very hard. We're going to go to a case now where the analysis is even harder. And the point about the Seiberg-Witten equations is they're sort of nastier-looking equations. They don't look quite as geometric. But that's not the point. The point is that the analysis is much easier, so you can do more with them. So I'm going to pass to some higher-dimensional gauge theory now, unless there's any questions. Okay. So if you remember, I mentioned these generalized equations of Tian, which sort of encompass all known first-order Yang-Mills equations. So these are these equations, star Fa wedged with some n-4 form is plus or minus Fa. And there are, I guess there'll be a lecture of Conan Lung's next week on work of his and Lee's on more general sort of gauge theory equations, setting everything in a general framework of special holonomy and cross products. So that'll make a good link with Robert Bryant's lecture. This will link more with Blaine Lawson's. So Tian's given a link between these connections. I'm thinking of them usually in higher dimensions, but these include, of course, all the lower dimensional cases. If I take omega to be 1, we get the anti-self-dual equation on a 4-manifold. And calibrated geometry. So we get these estimates on the as I've tried to make clear, the L2 estimates you get, the topological you get these topological estimates for the L2 norm of the curvature just from the equation, just from those rearrangements of the Yang-Mills functional, and the fact that they're absolute minima. And using this, you get sort of compactness type, weak compactness sort of results about the moduli space of solutions. So that was to do with the number of bubbles which came off in the 4-dimensional case. So this extends to higher dimensions in some sense. So you can show, so this is work of Tian and more recently Terry Tao and Tian. You can show that sequences of these connections converge. Firstly, I think this is well known for a long time. People like Uhlenbeck and Nakajima knew this. That they converge away from something, from some bad set, which I'll call Z, of finite Hausdorff codimension 4. So these are the finite number of points in a 4-manifold. Okay, so the local model you're supposed to think of is that you're getting blow-up, you're getting one of these Dirac delta blow-ups inside R4 times by Rn minus 4 to bring you up to n dimensions. So you're getting a blow-up locus of a point times Rn minus 4. So you're getting some Rn minus 4 blow-up locus. That's the local model to keep in mind. Then he does lots of things I don't really understand, but he shows that he does lots of blow-up analysis. So you rescale, you rescale perpendicular to this. I guess you don't do that quite yet. So he shows lots of technical results. So this blow-up locus is rectifiable, which means almost everywhere tangent cones exist. And you blow up perpendicular, so you expand perpendicular to this blow-up locus. So that's the inverse of this conformal invariance I was talking about before on R4. So we're just stretching this R4, leaving this alone as we look at this sequence of anti-self-dual connections. And if you blow it up at the right rate, you can get a limit anti-self-dual connection, which is non-trivial, it's non-zero, but it's also smooth. And what you find is the limits are, I'm just blowing up at one point. I'm analyzing a point of this blow-up locus, and I'm rescaling everything so that it doesn't look like this anymore, it looks smoother. And what you find is the resulting thing that you get just on this tangent space is an instanton, so a solution of the anti-self-dual equations on R4 times by Rn minus 4. This is just the local analysis around one point of this bad blow-up locus. And then from just linear algebra, you'll be able to show that this direction along which this bad locus lies, along which these peaks lie, is actually calibrated by your calibration form omega, just from this equation. So this equation holds in the limit, and therefore it follows that this Rn minus 4 is a calibrating submanifold of the tangent space at this point, which is Rn. So that goes as follows. So you write your form as some multiple of the volume form on this piece. This is of course the tangent space at some point P T blah. Plus something which restricts to 0 on this piece. But that's not necessarily a pullback of a form on this piece, right? It could be mixed. It could be a wedge of forms on this piece times forms on this piece. But it's something which, on restriction to here, is 0. Okay, so you're restricting something to here, and it's becoming a top form. So if there's any mixed pieces, then it'll restrict to 0. And then you can just rewrite that equation in this form. And what you find is that this alpha actually has to be plus or minus 1, so that the omega is restricting to this tangent space to be the volume form. So it really is calibrating this tangent space. So at each point you have a calibration. So the reason for that is FB is, you get this equation, and if you do it twice, you find that alpha squared equals 1. You just do that equation. Do star and multiply by alpha on this side, and you find that alpha squared is 1. Okay, so at least at the smooth points of this blow-up locus, you find it's a calibrated submanifold. And then we have some more technical stuff. And the L2 estimates, remember before we had bubbles at a single point, and they were contributing, in some sense, 1 to the second Chern class. Here, the appropriate charge or mass is the volume of this calibrated submanifold gives you second Chern class in your bundle. So you, every time you, well, I haven't told you the removal of singularities theorem yet, have I? But I mean, the first thing you can say is that the mass of this calibrated cycle, so this is like the number of points in a 4-manifold where you have bubbles, is less than this charge of the bundle. And he has similar results for the second-order equations. There, what you find is that the subvariety, the current, in fact, where everything blows up, is no longer, of course, calibrated. It no longer satisfies a first-order equation. It satisfies a second-order equation, just like the generalized Yang-Mills equation. And that second-order equation is that it's stationary. So its mean curvature, distributional mean curvature vanishes. So, sorry, I was getting a bit ahead of myself here. So this is what I was referring to before. So he actually also proves the removal of singularities result. This is also jointly with tau. That so what you'd like to do is think of your sequence of connections as converging to something with a bubble along this calibrated cycle, which you then remove and get an anti-self, one of these omega anti-self dual connections away from that bubble extending over Z. So you'd like the limit of a bunch of omega anti-self dual instantons to be another omega anti-self dual instanton on a bundle with lower second Chern class, plus some Dirac delta concentrated along this calibrated submanifold. So you should say tau. And Tian and Tau show that this is true, at least on the top stratum. So we can remove, so Z is Hausdorff n-4 dimensional. We can remove the n- something of n-4 dimensions from it to leave something of smaller dimension. And away from some nonsense and singularities of even smaller dimension, we can indeed extend the connection over this Z. So we can extend it over at least the top stratum of Z in some sense. And that's enough. That means we've got the thing defining codimension 4, so that's enough to define the second Chern class. Second Chern class is just a codimension 4 object. So we can get a bundle on the limiting, we can get a bundle which is sort of the limit of these connections, with the bubble removed, at least away from something of codimension 5. So that's enough to define its second Chern class. And then you find that, indeed, the second Chern class dotted with omega of this new bundle differs from the second Chern class dotted with omega of the old bundle by the mass of this calibrated cycle. So the integral of omega over it times by the appropriate multiplicity. So this is the beginnings of the kind of compactness result, which I mentioned for anti-self dual connections in 4 dimensions. So you want to consider connections plus these ideal connections, these Dirac delta bubbles along calibrated submanifolds. But there's work still to do. So, I mean, really, I'm not saying particularly much about calibrated cycles and gauge theory, other than it's clear there's an analogy there. But there really isn't much that's been done. The analysis in high dimensions is very, very difficult, and not a great deal has been proved yet. So there's a lot of formal pictures. There's a lot of beautiful things you could do with these gauge theories if you could define them, if you could define invariants from them. But the problem is this hasn't been done. So it needs good geometric analysts like you lot to sort out all the foundations of the subject. So pretty much any theory that you have in gauge theory, there's a corresponding theory in calibrated cycles, at least formally. There's Floer theories in gauge theory, which I haven't had time to tell you about. There's corresponding Floer theories in the theory of calibrated cycles. There's certain gauge theories which come as critical points of a functional, things like the Chern-Simons functional. There's appropriate functionals on the submanifold side as well. These things are very, very closely related. Under mirror symmetry, they're often supposed to be the same thing in physics. So Hermitian-Yang-Mills vector bundles and perturbations of those, called the the MMMS equations, are supposed to map under mirror symmetry from one Calabi-Yau manifold onto another Calabi-Yau manifold, where they become special Lagrangian cycles, so certain calibrated cycles with a flat vector bundle over them. So there's a great deal of interaction between these two subjects, but very little of the analysis has been done. In fact, there's a great deal has been done on both sides, but not enough to define the analogues of Donaldson theory and so on and so forth. Now, there's one case where you can do something, and that's where you can use algebraic geometry. So pretty much the only one of these higher dimensional gauge theory equations which admits a purely algebrogeometric interpretation, at least via the Donaldson-Uhlenbeck-Yau theorem, is a certain 3-dimensional gauge theory. So I've actually avoided telling you about the 3-dimensional theories so far, and flat connections on 3 manifolds, and that's because I want to explain it now, and its holomorphic analog in 3 complex dimensions. So this is another gauge theory. This is called Chern-Simons theory. This is another example. So Taubes has a definition of the Casson invariant, which is purely gauge theoretic. And roughly speaking, it counts flat connections on a vector bundle on a 3-manifold. This is a 3-manifold. So I'm on a real 3-manifold. So the formal picture is the following. So on the space of all connections, this curly A here, there's a closed one form. So what's a one form? It's something which pairs with tangent vectors. So tangent vectors lie in here, clearly. This is the tangent space to this. And what's the value of this one form, the curvature, on tangent vectors? It's the following. So you just integrate the tangent vector against the curvature. That gives you a 3 form, take its trace, integrate over the manifold. So that clearly gives you a 1 form formally on this infinite dimensional space. It turns out it's gauge invariant. So it descends to connections modulo gauge. And because it's it turns out it's closed, that's very easy to see. Essentially has constant coefficients. No, that's not true. No, it's not so. It's a calculation that that's closed. So locally, at least, it's the derivative of a function on this space of connections. And that function is the Chern-Simons functional, which is given by the following formula. If you pick a base point, define the function to be 0 there, and then this defines it on all other connections. So it's just some formula. It doesn't really matter what it is. But it actually this is gauge invariant and makes sense. And the reason for that is the following. It actually has makes some topological sense. It's like an eta invariant. It's a transgression of the second Chern class. So what I'm describing here is this paragraph. So if I have a 3-manifold with a connection A on a bundle, because the cobordism ring's trivial, I can bound it by a 4-manifold. And let's extend the bundle over the 4-manifold and the connection. So I end up with some bundle here with some connection on it over the 4-manifold. And then this Chern-Simons functional turns out to be the integral over the 4-manifold of the characteristic class representing the second Chern class. Maybe P1. There's a plus or a minus there. So this is not an integer because I'm integrating on a manifold with boundary. And then this is why it's gauge invariant. Up to, you see, if you chose a different 4-manifold, and primed here, and a different extension, then you could glue the two extensions together, get a connection over the whole compact 4-manifold. So this is the integral over n primed of the same thing, plus or minus the integral over a compact 4-manifold, which is n union n primed of this C2 here. So this is an integer. So this is independent of the 4-manifold you choose and the extension you choose up to an integer. Okay, so this is a gauge invariant up to an integer. For gauge transformations connected to the identity, it is completely gauge invariant. For non-homotopic, the identity gauge transformations, you can pick up an integer. So really, it's a map to a circle. Anyway, so formally, we have a function on a manifold. It's infinite dimensional, but never mind. So you might try and do Morse theory with this function. So the first thing you would do is look at its critical points. And the number of critical points ought to be the Euler characteristic of the manifold. So this is the number of zeros of this covector field, this one form. So that's formally, you're trying to make sense of the Euler characteristic of this infinite dimensional space of connections. The number of zeros of this covector field, the derivative of this function. But that's the number of flat connections. So that's connections with zero curvature. So formally, that's what you'd like to do. Then you can extend that and try and do Floer theory, which is actually where you do Morse theory with this functional. So you take gradient flows of these functionals between these different critical points. And that I haven't got time to talk about. Now, let me just explain one little thing here. If you're at the if you're at a critical point of a function, so you have df is 0 at some point p. Let's say we're in finite dimensions here. Then you can differentiate this to take the Hessian of this function. Because df vanishes, this is sort of independent of your choice of connection or way of differentiating by the Leibniz rule. So this is a map from... So the derivative takes a tangent vector that we're going to differentiate along of your manifold, and it gives out the derivative of df along that. Well, df is a 1 form, so it gives out a 1 form. So it's an element of T star tensor T star. And it's symmetric as an element of this. It's actually an S2 T star. That's just the same that partial derivatives commute. D by dx, d2 by dxy is the same as d2 by dyx. So the Hessian is symmetric. So the deformation complex of the zeros of this 1 form, that's given by this is the 2-term deformation complex. The kernel here is the tangent space, the space of critical points. The co-kernel is the obstruction space. And this complex is self-dual. This map here is dual, which goes from the dual of this space to the dual of this space, i.e. from T to T star, is exactly the same map. So you end up with so all this formal nonsense, which is all in infinite dimensions, has a finite dimensional manifestation, which is that the deformation complex of flat connections is actually self-dual. So when you do the deformation complex, which I've written down before, it turns out you get a map here from this would be the space of connection, so this will be 1 forms with values in SU of E or something, to 2 forms in SU of E. Formally, these spaces are dual because there's some integration between them. You can take a 1 form and 2 form, wedge them together, take trace, and integrate. And this map that you get, which will be dA, is actually self-dual. So when you take the dual space there, and the adjoint map, it turns out to be the same map. In particular, cohomology groups are self-dual, and that's just Poincare duality. The H1 is dual to H2, and so on. So that's at least something rigorous, you can say. And in particular, what that means is that the virtual dimension of the moduli space is actually 0, because all of the terms in there cancel with each other, because they're dual vector spaces. Okay, so that's so we can really make rigorous sense of why we expect a 0-dimensional moduli space. So we expect to count flat connections. So we're not expecting a higher dimensional moduli space. So we can try and count flat connections to make some formal sense of this. So the Casson invariants, actually, you're supposed to count them minus the trivial connection. You're not supposed to count that, and then you're supposed to divide by 2. Turns out you get an even answer, you see. So, and that's formally the Casson invariant. But as far as we're concerned, we're just counting these flat connections. Okay. The original definition of Casson can also be sort of seen in these terms. So what he does is he splits the manifold along a surface. So a picture like this, but in 1 dimension lower. So here's this 3 manifold, and he splits it along a surface, which is a 2 manifold. So he has M1, M2. It's a gluing of 3 manifolds with boundary. And he looks at flat connections on this surface. And because the surface is symplectic in an obvious way, because there's a volume form, then the moduli space of flat connections on the surface also turns out to be symplectic. And it turns out that these maps of, you may know that the restriction map like on first cohomology from here to here gives you a Lagrangian subspace of the first cohomology of the surface, which is naturally symplectic. This is the non-abelian version of that. Don't worry if you don't know that. But what it turns out is when you take a flat connection on M1 and you restrict it to the surface, that gives you a map from the moduli space of flat connections on M1 to the moduli space of flat connections on S. And that gives you a Lagrangian subspace of this symplectic manifold. So something, this is actually slightly singular. So it gives you something half-dimensional. And what you do is you intersect these 2 half-dimensional submanifolds. So you expect a finite number of points. And what is an intersection point? It's something which is on both of these moduli spaces inside here. So it's a flat connection on S, which extends both to M1 and to M2, because it's in the image of both restriction maps. So it's a flat connection on the whole 3 manifold. So formally, you can think of the intersection of these 2 half-dimensional subspaces as being the space of flat connections. So that was Casson's original definition. He showed by some perturbations and so on, you could make sense of that and get an invariant. Now, there's a formal higher dimensional version of all this in 3 complex dimensions. And it turns out you need to be on a Calabi-Yau threefold. So this is something, instead of being on an oriented, I guess I forgot to emphasize these 3 manifolds are oriented. I'm integrating everywhere, so I'm integrating against an orientation. I need to do that on the threefold. What I do is integrate against a complex orientation. So that's this Calabi-Yau form. Theta is dz1, wedge dz2. Where's dz3? Or z, as you call it. So a Calabi-Yau is something where this makes sense. So the canonical bundle, the third wedge of the holomorphic cotangent bundle is trivial. It has this trivial holomorphic section. So we pick that, and that's what we're going to integrate against. That's the complex orientation. So naively, you just complexify everything, replace integration against the orientation by integration against this theta. And we work, instead of with connections, with d-bar operators. So instead of with dx's, 1 forms, we work with 0 1 forms, dz bars. Okay, so we've talked about that before. And what you find is exactly the same picture holds. So there's a closed 1 form, and this time it's given by the 0 2 part of the curvature. I just integrate it against the 0 1 form. which is the tangent space, the space of d-bar operators. That gives me a closed one form. Again, that's gauge invariant. It's actually locally d of a function. That function is a holomorphic Chern-Simons functional, which looks very similar to the one before. That also has a topological interpretation in terms of complex fourfolds, but I haven't got time to go into that. But there is, you can look in the notes, there is indeed some kind of interpretation. This functional, again, is defined up to some periods. They're worse than integers this time, but it doesn't matter. We can still talk about its critical points. And its critical points are where this one form vanishes. So they're d-bar operators such that d-bar squared is 0. 0 to part of the curvature is 0. But they're just holomorphic bundles. And formally, again, the deformation complex, therefore, of the space of holomorphic bundles or holomorphic structures on a fixed topological bundle on a Calabi-Yau threefold turn out to be self-dual. So the deformation complex is self-dual. The cohomology groups are all dual to each other. So they all cancel out, and you get that the virtual dimension is 0. So H1, the endomorphism, is isomorphic to the dual of H2. So the deformation space, the tangent space, is isomorphic to the obstruction space. So ideally, you expect to get a zero-dimensional moduli space only on a Calabi-Yau threefold. So you'd hope to count them, i.e. to get the Euler class of the cotangent bundle of the Euler class of this one form is a section of the cotangent bundle. And again, there's an analog due to Donaldson and Turin of the original of Cassin's, a complex analog of Cassin's original definition of the Cassin invariant via Heegaard splitting. Here you use a normal crossing Calabi-Yau manifold. So you're supposed to degenerate your Calabi-Yau manifold to something which looks like a union of two other pieces, intersecting along a complex surface, which will be a K3 surface. And then you look at, so this will be K3 surface, be a Calabi-Yau in dimension 2, and therefore it's holomorphic symplectic, therefore its moduli of bundles is holomorphic symplectic. And what you find is that, again, the restriction maps taking holomorphic bundles on these two pieces to holomorphic bundles on the surface give you complex Lagrangians inside this holomorphic symplectic manifold. And so you can intersect them. Again, that is purely formal. This has not been rigorized. No one's managed to rigorize this yet. That's a good algebra geometric problem to do with defining modular bundles for degenerated varieties. So I want to try and show you how to define. I guess I'm running out of time, so I'll just very briefly do this. So you want to try and define this holomorphic Cassin invariant by counting holomorphic bundles on a Calabi-Yau threefold. So we need to compactify, or we need to find a compact moduli space. So we first have to restrict to stable bundles, otherwise we get something horribly infinite. And then you could try and use Tian's theorem, but as I say, that's we haven't got far enough yet. In particular with transversality, the analysis isn't good enough to be able to get a zero-dimensional moduli space. So you can't perturb the equations and keep compactness and so on, and understand compactness well enough. So what you have to do is use algebraic geometry and something called virtual moduli cycles. And since I haven't got time, if anyone's interested, they're all on the notes. If anyone hasn't got any notes, ask me. And if anyone's interested in this and can't understand it on the notes, then do come and ask me, and I'll explain it. Because otherwise I won't have time to do Seiberg-Witten. So, okay, so I'll end very briefly with an example, since we haven't calculated many examples. Anyway, it can be done rigorously. We can count the number of holomorphic bundles on a Calabi-Yau threefold. So here's a very pretty example, which is easier than it looks on the slides because I can draw it. So you take a quadric in CP5. You take three of them, in fact, Q0, Q1, Q2. But I'm going to work inside Q0. So I'm not really working inside CP5. I'm working inside Q0, which is a fourfold. And then inside there, I've got Q1, intersect Q0, and Q2 intersect Q0. And their union is in some sense a singular Calabi-Yau, and then their intersection, which is Q0 intersect Q1 intersect Q2, is a K3 surface. Now, all of these quadrics are actually isomorphic to the Grassmannian of two planes in C4, and so they have universal two-plane bundles over them, the subspace bundle and the quotient bundle. So associated to every single one of these quadrics, you get two vector bundles. So if you're on this K3 surface, that is the intersection of all the quadrics in this linear system. There's a whole P2 of them. So any linear combination of these quadrics gives you a Grassmannian and gives you two bundles on this K3 surface, which is contained in all of these things. So you actually get a double cover of P2. So you get a moduli space on the K3 surface, which is a double cover of P2. So for every point of P2, I get two bundles. Every point of P2 is a quadric through this K3. There's two natural bundles on that. I restrict them to the K3, and I get two different bundles on that K3. And it's branched over a sextic curve where these quadrics become singular. You can work that out. It's in the notes. And so this is actually itself another K3 surface. Similarly, the moduli space of bundles on this is X1, this is X2, is a double cover of a line inside P2. So what are the quadrics which go through X1? They're the linear span of Q0 and Q1. They're the P1 combinations of these. So every point of P1 gives you two bundles, so you get a double cover of P1. Similarly for MX2. So double cover of a different P1. This was the span of Q0 and Q1. This is the span of Q0 and Q2. So that Casson invariant of Donaldson-Turin says you should intersect. You've got these two complex Lagrangians inside this complex symplectic space. Everything's double covered here. And you just take their intersection. So you've got two P1s in P2. You take their intersection, you get 1 point. Actually, when you take the double cover, you get 2 points. And what that amounts to is the two bundles on Q0. So what you end up with is that the Casson invariant of this singular Calabi-Yau is 2, you would hope, given by the two bundles on Q0. And that is actually true, so you can then smooth everything and get this theorem. So this motivates the following theorem, which is when you smooth this union here, so this is a quadric plus a quadric, when you smooth it to a quartic, you get the following. You find that indeed there are only two bundles on that smooth Calabi-Yau manifold. They are the two bundles coming from Q0, and the corresponding holomorphic Casson invariant is 2. Okay, sorry I had to rush that, but I wanted to give you a little example in the end. Thank you.